So as mentioned in the previous video, we're continuing the analysis of the SO2 in the recovery border. We were wondering if the sensor was broken or there was something else that was happening in the process. So what we're going to do, we're going to open the other module, which is the global analysis. The global analysis is actually using the PCA algorithm. So what we're going to do here, we can name the model. So we have by default the date and then a numeration of the PCA. We can use all the variable, or we can decide to remove few of them. So here I'm going to keep that, add, and build my PCA. So what we say usually is you need to have a question when you do that kind of analysis, and you can use you can finish the cleaning in the PCA, but once it's done, you have to go back to your question. Here we can see that the hotlink t-square is showing few observations that should be removed, and as well as the SPE. So the hotlink is calculated with the components that we see here. That's the accuracy of the model increasing with the number of components that are kept in the model. If we want to know what is a component, we can click on one component. And we're going to have the loadings and the scores. So the loadings, what is the loadings? It can be seen also as it's from the eigenvalues and eigenvectors, and they're gonna help to put more weight on some variables according to their influence in the dataset. So it's using covariance. We won't go too far in that video, but there's many other videos that are explaining what is the PCA itself. Here we're gonna focus more on the use, how you can use that as a tool to do troubleshooting in your plant or cleaning the data as well. So as I was saying, we can finish the cleaning, so we can still clean here, and you can see that selection that is done in the other charts. So we're going to construct a new one without those observations. And I will save the new model. So you can see we have something that is a little bit closer. We didn't clean too much here. We could have cleaned more, but since we're doing troubleshooting, we won't do too much cleaning. What we want to know, if we remember, was the difference. It's kind of knowing the difference between the high value of SO2 and the low value of SO2. So what we're going to do, we're going to create two groups. And those groups with criteria, they can be, I went a little bit quickly, but by using that menu, or you can also go in that one and create new groups. We're going to select variables, and from the SO2 we want to know the difference between the highest and the lowest. And so with two groups, we should be okay. Can change the color because I know that some people have a little bit more trouble with the other color. And we have our two groups and the correlations of our observation. And we can see that we have in the scores a good separation. And if we want to check with the loadings here, we have the SO2 here, and we can see that the highest values of SO2 are near the loading of SO2. At the opposite, we should expect lower values for those variables that are temperature around the superheater. So if we try to have if we want something easier to do the interpretation of those information, what we can do is by using a chart of observations like t-square, SPE, or scores, we can perform a group analysis. So that group analysis, we can select those two groups and perform the calculation with contribution. So we have our contributions that are calculated. We have the t-square with the calculation, the contribution of t-square, the one SPE, and scores. So what we're going to do is expanding that one, and we can see here that we have for that group a little bit higher value than the average usually for that variable, and fairly lower values for that one. And on the other side, we have the SO2, where we have a higher value for that group and a lower value in that one. That was the variables that we have used to create our group. So it's not a surprise to see that difference. And the black series is actually the difference between the two groups. But we want to know what does it mean really. So if we click on the variable, we're going to have actually the time series of that variable. And we can see here that finally we were not able to see it at first, but there's quite something. And it seems to be a little bit related with what happened in the process. So is it the same thing with other variable? Oh, yeah, kind of, eh? We still have another, it's not as pronounced as the other one, but there's still something, and on that one as well. So even though it's not a clear answer of if the sensor is broken or not, it seems that several variables indicates that the process wasn't in a normal operation when those emissions happened. And on the other side, we can see that the pressure for air had increased along that period. So even though in few minutes you can have a quick idea if the process was working well last week, and this week it doesn't work well, you can check the difference between it was going well, it's not going well. What's the difference? And we're going to see later in the monitoring how we can use the T-square modeling in the SPE for process monitoring and fault detection online. But before that, we're going to go see the predictive modeling, and again we can pass by here or the other menu, or closing here and reopening that one. That module is the predictive modeling. Why we would like to use that for our analysis? It's because it can help to explain what's happening in the process actually. So we're going to try to explain how the SO2 is what variables can have an influence or can help to explain what's happening with the SO2. So we're going to add our SO2 here, and we can select, or we can also actually select the dataset we had in the PCA, and the second one had an advantage because it was a little bit more clean. And we're gonna we have the selection that is done. We're gonna put the SO2 back in the Y grouping, and we're gonna build. So when we build like that, we build the PLS, but we also build a neural network in the back. So at first we seem to have a very good prediction, and here we have the blue stripes, that is the R square, and the green, that is the Q square. So the blue is the training data, and the Q is the validation data. So we can see if the model is able to perform well outside of the training group. So we can go see in that the performance model. So we have it's a kind of a surprise, for we were expecting a little bit cleaner data set because we had a high coefficient of correlation, at least fairly high, but we can see that it's not, doesn't seem to be perfect. If we go further in the analysis, and here what we have as for the interpretation of that chart, we would expect we have the actual values here and the predicted values here. So in an ideal case, every dot would have been on the red line, which is obviously not the case here. We're going to see other tools here. It's regression coefficients and VIPs. So the regression coefficients here, it's kind of the slopes for each variable in the equation. But instead of having the slope itself, it's a normalized slope because all data are normalized. So when we have here a positive value, it means that that value has a significant influence. It's not because the scale of the value is 200,000 or 1%. It's not the scale that has an impact on the slope, but more the importance to predict it. So we can see that that one has more importance, and that one is also very important, but on the opposite way. So that has a great impact, but with a negative slope. And we can see at the bottom with the VIP here that that variable does have a high influence. And we have some other variables that could have had a bigger influence, but maybe that variable wasn't as linear as the others, so the others could have been more uh, um, they've been selected in priorly for the equation. We can go a little bit further here, and we have the predicted value compared to the actual values. And here we have the results for the neural network. And what we see here is a very high value for the neural network. And we have here on that chart the actual data in blue that we don't really see that much. We have the neural net that is kind of covering those blue values, those blue dots. And we have the PLS output, which is the green output here. So the PLS is not perfect, but still it catches up to show a kind of tendency, showing that there's actually something in the dataset that can explain the SO2 variation. And the neural network, even though could be a very, very good neural network, but the SO2 value is not part of the training values for the neural network. So if you wouldn't have information in the dataset, you couldn't have uh, something here that would have been able to explain the variation. And at the bottom here, you have the same thing, but with the external validation. So 20% of the dataset that was taken out to test the models. But we have quite a lot of data, and it could be a good idea to have a smaller model if we want to implement it. So to do that, we're gonna rebuild the model with less data. And to do that, we can do it either by selecting the VIP, the regression coefficient, or both, or a number of variable for the VIP. But here we can go with a combination according to the criteria. So if we want to keep more, we can do 0.8 in VIP and 0.1 in the regression coefficient, or we can do OR to keep more values. And we rebuild the model. So we've kept 12 variables. We still have quite a good model here, and a good Q2. Say OK. And if we go directly in the reduced regression coefficient in VIP, we can see which variables have been kept here and their importance in the prediction. And we can confirm that and compare the models. Here we can compare the PLS. So we have actual data, initial model, and reduced model. And we can do the same with the neural network here. So the next level is to actually oh yeah, maybe if you want to do to use the equation, you can export the model in an Excel file, and then you're going to be able to use it in your Excel file. That's an easy way to use the model. So the next step will be a simulation of the use of those models in a monitoring condition. We were going to simulate the application of those models in a plant. So it's going to be done in the next video. Thank you.